In this lecture, we want to continue talking about discrete random variables by moving into what are called binomial experiments. And then from binomial experiments, we'll talk about the binomial probability distribution. So this is the example we're going to work first in class, and it's going to help drive the concepts that we talk about. All right, so suppose the basketball player LeBron James. So I hope you've all heard of LeBron James. Okay. What he does is he makes free throws. In basketball, what a free throw is it's a free shot with nobody guarding them from a foul line. If you're unsure exactly what a free throw is, there's a link here that will take you to a website to explain it. But so LeBron James makes this shot 80% of the time. So the probability that LeBron James makes the shot is equal to 0.80. Okay. If LeBron James, a little bit of typo there, sorry. If LeBron James shoots 10 free throws, what's the probability he makes exactly 8 of them? So he's going to shoot exactly 10. And what we want to know, if he shoots exactly 10, what's the probability he makes exactly 8? So a lot of times when people see this type of problem, they say, well, if he makes them 80% of the time, or probably makes a shot is 80% or 0.80, what's probably he makes 8 out of 10? Well, it's got to be 0.80. So that's not correct. This problem is actually kind of complicated right now to figure out what it is. Because exactly how does he make the 8 free throws? Does he make the first 4, miss the next 2, make the last 4? Does he make the first 8, miss the last 2? So it's a little bit complicated. So right now we can't answer it. Okay, we're going to need eventually what's called the binomial probability distribution to do this. So our 2 objectives for this lecture, all right, besides answering this question, we will come back and this will be the first, big probability question we answer. We want to determine whether what we call a probability experiment is a binomial experiment, and then we want to compute probabilities of binomial experiments. All right, so first one, determine whether a probability experiment is a what we call a binomial experiment right here. All right, so the criteria. So a probability experiment is said to be a binomial experiment if the experiment is performed a fixed number of times. Well, in the LeBron James case, he's going to shoot 10 shots exactly. So it's a fixed number of time. Okay, notice I didn't say, hey, shoots until he makes 8. No, I'm saying he's shooting 10. So each repetition of the experiment is called a trial. So what this is, in the LeBron James example, there are 10 trials. All right. The trials are independent. This means the outcomes of one trial will not affect the outcomes of another trial. So in the LeBron James case, what we're going to do is we're going to assume that each time he shoots a shot, they're independent of each other. So if he makes or misses a shot, it's going to have no bearing on if he makes or misses the second shot. So for each trial, there are 2 mutually exclusive or disjoint outcomes, and 2 outcomes we call our success or failure. So in the case of our problem, a success, quote unquote, would be that he makes the shot, he makes the free throw, and a failure would be that he misses the free throw. All right, and the probability of success is fixed for each trial of the experiment. So the probability of a success here, well, that's the probability he makes the shot. That's equal to 0.80. All right, so in the LeBron James case, it looks like, in the LeBron James example, it seems like the problem that we have here can be modeled as this binomial experiment. All right, so here's some notation used for the binomial probability distribution that we're going to get to, and I'll show it with the LeBron James case too. All right, there are n independent trials of the experiment. So LeBron James is going to shoot 10 free throws. We're going to let P denote the probability of success, which is 0.80. The other probability we're going to need is this 1 minus P. That's the probability of failure. So 1 minus P in this case is 0.20. We're going to let X be the binomial random variable that denotes the number of successes in n independent trials. So X is going to be the number of successes. All right, so if you think about it, we wanted LeBron James to make 8 of the free throws. Also, what you'll notice in the coming slides, we're going to have this thing called n minus x. Well, this is going to be the number of failures. And in this case, we want LeBron James to miss 2 of the 10. Okay, that's how many failures we have. And we're going to use these 5 numbers here, all right, in a formula in a little bit. All right, but before we do that, let's just make sure we understand exactly what binomial experiments are. So which of the following are binomial experiments? So a player rolls a pair of fair dice 10 times. So he's going to do it, he or she's going to roll 10 times. So that's fixed. Okay. And what we're going to do is we're going to record X as be the number of 7s rolled is recorded. Okay, so 7, we're going to sum the dice. So this is a binomial experiment. Okay. Going back, it meets all 4 of these criteria. We're going to fixed number of times, trials are independence. There's only 2 outcomes. We're counting if you get a 7 or you don't get a 7. And the probability of rolling a 7 on this pair of sum dice, it never changes. All right, so this one here. The 11 largest airlines had a an on-time percentage of 84.7% in November 2001. So in order to assess reasons for delays, an official with the FAA randomly selects flights until she finds 10 that are not on time. Okay, the number of flights X that need to be selected is recorded. So this person's going to select until she finds 10. So we don't know if that takes her 10 times, 11 times, 12 times. So this is not a binomial experiment. It's not a fixed number of trials. All right, so which of the following here, if this one is? So in a class of 30 students, 55% are female. The instructor randomly selects 4 students, and the number X of females selected is recorded. Well, because there's such a small sample size here, all right, this is not a binomial experiment because the trials are not independent. Because after you select the first person, it's going to change the probability, that you select a female next. Okay, so it's not independent here. So we're only going to deal with cases like this first one here. Okay, we've got to make sure that it meets all 4 of these requirements. All right, so now how do we compute probabilities of binomial experiments? So the probability of obtaining, I know this formula looks a little crazy, and I'll talk about it in a second. So the probability of obtaining X successes, so like LeBron James scoring 8 free throws, all right, in N trials in 10 shots of a binomial experiment is given by, so it's the probability of X, okay, is equal to, the first thing we have to do is we have to do N choose X. This counts the number of ways that you can have X successes in N trials. Okay, so in the LeBron James case, the order, none of this order matters here because we don't care how he makes the free throws and what arrangements he does. So this is going to be a number, N choose X. Then we're going to multiply it by the probability of success P raised to the number of successes. And then we're going to multiply this, so multiply. 1 minus P is the probability of failure raised to the number of failures. Okay? So if it helps to see it, it's N choose X times probability of success raised to the number of successes times the probability of failure that number raised to the number of failures. Okay. So what I'm going to do here in this slide first is I'm going to show you how to do this formula by hand with the not with hand, but with your calculator. And then in the follow-up lecture to this, I'm going to show you how to just use a little bit of a cheat function in your calculator to do the exact same thing. So first we'll learn how to use the formula in depth, and then we'll follow that up with the little bit easier way in your calculator. Okay, so going back. Suppose a basketball player LeBron James makes free throws. If LeBron James shoots 10 free throws, what's the probability he makes exactly 8 of the 10? So the formula was this. It's the probability of number of successes, X. It's just N choose X times P to the X times 1 minus p to the n minus x. So in the LeBron James case, remember n was 10, x was 8, p, the probability of success, was 0.80. 1 minus p, the probability of failure, was 0.20. And then the number of failures was 2. So for this problem, you would just write it like this. It would be the probability you get 8 successes. So it would be 10 choose 8 times the probability of success, 0.80, raised to the number of successes, 8, times probability of failure, which we saw was 0.20, raised to the number of failures. All right, so grab your trusty calculator for this. Okay. So we need to do 10 choose 8. So 10 math, go over to PROB or PRB, depending on your calculator. NCR, you're going to go 10 choose 8. That's 45. You're going to multiply that by 0.8 raised to the 8th power. Oh. So times, sorry about that, 0.80 raised to the 8th power. Now you're going to multiply that by 0.20 squared. And the probability that LeBron James would make exactly 8 to the 10, it's 0.30. I'm going to round it to 2. So it's only a little over 30%. Right, the reason it's not, higher than that is because he could make 9 of the 10, he could make 10 of the 10, he could make 7 of the 10, he could make 6 of the 10, he could make 5 of the 10, and so on. So you have to account for all those different probabilities too. So that's why this one is only just barely over 30%. Okay, let's do another one here. Okay, before we do that, I'm sorry. Let me do some common mathematical phrases. That'll come up when we do these type of probability questions, just so you know the excuse me, the equality or inequality they'll use for this. So when you see words like at least or no less than or greater than or equal to, you're going to use the greater than or equal to sign. When you see more than or greater than, okay, that's going to be the strict greater than sign. Okay, so it needs to be more than, it needs to be greater than. Fewer than or less than is the less than sign. No more than, at most, or less than or equal to, you're going to use the less than or equal to sign. And exactly or equals or is, you're going to use the equal sign. So these are common phrases that'll come up in these binomial questions. So, keep this handy so you'll know which one of these symbols to put into your probability statement. Okay, so this will be the next example we work with. According to the Experian Automotive, 35% of all car-owning households have 3 or more vehicles. Okay, so what that means is the probability that a household has 3 or more vehicles, or 3 or more cars, excuse me, is equal to 0.35. So I'm not in that household. My household does not have 3 or more cars. So in a random sample of 20 car-owning households, what is the probability that exactly, so you see the word exactly, tells me it's going to be an equal probability down here. What is the probability that exactly 5 have 3 or more cars? Okay. So it's the probability that, I'm going to write it 2 ways. You can write it as probability you get a 5, or you could write it as the probability of the number of successes is equal to 5. Okay? So you're just going to use this formula. Okay? So remember, it's n choose x times p to the x times 1 minus p to the n minus x. Okay? Always, always, always. Okay, so what you're going to do is you want to find the number of households in 20. Okay, the probability that the number of households in 20 that have 3 or more cars is exactly 5. So exactly 5 of the 20 households have 3 or more cars. So you're going to do n is 20. I want exactly 5 of the households. We know the probability that a household has three or more cars, it's 0.35. Raised to the number of successes, 5. Probability of failure, 1 minus p. So this would be 1 minus 0.35, or, this is also 0.65. Raised to the n minus x, which would be 20 minus 5, which would be 15. So let's verify with our calculator that we get this answer. So it would be 20, choose 5, times 0.35 raised to the 5th power, times 0.65 raised to that 15th power. So 0.1272 when we round it. And we got it right there. So this works. All right, let's do this one here. So again, according to Experian Automotive, 35% of all car-owning households have 3 or more cars. So in a random sample of 20 households, what is the probability that less than 4, all right, have 3 or more cars? So less than 4. So when you see this less than sign right here, less than words here, excuse me, you see less than right here, tells me it's going to be a strict inequality. So I want to find the probability that the number of successes, the number of households that have 3 or more cars, is less than 4, which would be the same thing as the probability that x is less than or equal to 3. All right, so this is careful. You got to be careful with this. So the number of ways that you can be less than or equal to 3 is you could have 0 of the houses have 3 or more cars, or 1 of the houses, or 2 of the houses, or 3 of the houses, okay? So that's how you get the probability of 0 plus probability of 1 plus probability of 2 plus probability of 3. So the probability of 0, okay, so you want 0 successes. Well, that would be 20 choose 0 times the probability of success is 0.35 raised to the 0 power times 0.65, which is the probability of failure raised to the 20th power. Well, 20 choose 0 is 1. 0.35 to the 0 power is 1, so that's just 0.65 raised to the 20th power. What this means is, when you see something like this in your calculator, it means move the decimal place over 4 places. So 1, 2, 3, 4. It's 0.0002, basically, when we round it. Probability of 1. Now we take 20 households. We want to only choose 1. Times 0.35 to the 1st power times 0.65 now to the 20 minus 1, which would be 19th power. So 20 choose 1. You'll see that this is just 20. Okay, times 0.35. Times 0.65 raised to the 19th power. And that is 0.195, so I'll just do 0.0020. Probability of 2, well, this would be 20 choose 2 times 0.35. Now we want 2 successes times 0.65, and we want 18 failures. So 20 choose 2 times 0.35 squared times 0.65 to the 18th power. You get 0.00998, so 0.0010. Now let's do the probability of 3. So this would be 20 choose 3 times 0.35 to the third power times 0.65 to the 17th power. So 20 choose 3 times 0.35 to the third power times 0.65 to the 17th power. And that's going to be 0.0323. But I'll keep it as 0.0322. So now when you add all these up, that's how we get this same answer right here. So I know using the formula was a little complicated. So what I'm going to do in the follow-up next lecture is, I'm sorry, let me do one last quick problem before I go on. I got a little ahead of myself there. So now, in a random sample of 20 car-owning households, what is the probability at least 4? So at least here. So remember in previous problems, or in previous lectures, whenever we saw at least, we use the complement rule. Have 3 or more cars. I'm sorry, have at least 4. At least 4 of the households have 3 or more cars. So it's a probability that at least 4. So when you go back, you see this at least, it's a greater than or equal to. So this is just equal to 1 minus the probability that you have less than or equal to that number. So that would be less than or equal to 3, which is what we just found in the previous slide. So 1 minus that would get us 0.9556. So sorry for skipping this problem ahead, but what I was saying is what I want to do in the follow-up video here is I'm actually going to show you how to do a problem like this and like this a little bit easier in your calculator. So I'll show you how to do it on both a TI-83 and a TI-84. And I'm going to come back and I'm going to answer this question in that video.